Hi everyone. This is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today in this session, I want to explain about springs, important terms and definitions related to springs topic. So already the design and the problem solving we have already discussed in the previous sessions. So in this first definition is spring. What do you mean by spring? And what are the applications of a spring? And how do you classify the springs? And various terms related to the springs we will discuss in this session. So first of all, a spring, it is an elastic body. So already you know the elastic property. So when the load is applied on a material, it elongates some value, some time, and then it deform to differently. So whenever you remove the load, so it regains its the original shape. So this property is called as elasticity property. So plasticity is reverse of this elasticity property. So already we have discussed in the mechanical properties of materials. So the best example for this elasticity property in the material body is a spring. So the spring classified as a elastic body. So its function is to distort when loaded and to recover its original shape. So whenever you remove the load, so that is the definition of the spring. So what are the applications of spring? To use it to store the energy. So the springs are used to measure the forces in automobile engines for valve opening and closes. So many applications are there. Springs in the vibrations, vibrating machines to control or to remove, to reduce the amplitude of the vibrating body and to absorb the energy. So like this, applications of springs are there. In mechanical engineering, in automobile sector, the springs are very widely used for shock absorbers and for the dampers. So the types of springs are mainly classified as helical springs. The helical springs are made up of a wire coiled in the form of helix. So the wire is form in the form of that in the shape of helix with some angle, some helix angle. We will discuss later. So it is intended for compressive or tensile loads. So the cross section of the wire. So the cross section of the wire is circular one. So which is spring is made may be circular or rectangular. So generally the circular springs are widely used. So it may be sometimes a rectangular cross section also available. So that the cross section of the spring. So the spring cross section or you can see in the figure in helical springs. I will show you. So sometimes it may be used rectangular also. So that is depends upon the application. See in this figure shown the circular cross section helical spring. The spring is circular cross section shown. The two forms of helical springs are there again classified as compression helical springs and tension helical spring. So in figure A shown the compression helical spring and figure B the tension helical spring. So shown in this figure, the major terms are here. These are called coils and then wire cross section and the capital D is major mean coil diameter and the small d is the wire diameter So similarly in tension helical springs also. So these two types of springs are used for mechanical applications. So that is depends upon loads. The helical springs are said to be closely coiled. So when it is said to be closely coiled, when the spring wire is coiled so close that the plane containing each turn is nearly at right angles to the axis of the helix, shown in a figure, and the wire is subjected to torsion. So very close coiled, so close to that plane of angle. So in other words, the closely coiled helical springs and helix angle is very small. So it is usually less than 10 degrees. The helix angle, you can say in closed coil springs, 10 degrees only. These type of springs are called as helical, closely coiled helical springs. So whereas in open coiled helical spring, so the helix angle is large. When compared to the closely coiled, the helix angle is large. The spring coil wire is coiled in such a way that there is a gap between the two consecutive turns. So one turn to another turn, so that there is a gap. There is a gap between these two coils. So in case of closed coil springs, not like that. So it is very close to each other. The helix angle also very small in case of closed coiled helical spring. In a open coiled helical spring, the angle is when compared to the closed coil very high. So next type is torsion springs. So these type of torsion springs are widely used in electrical mechanisms. The springs may be of helical or spiral type. I will show you the figure. So the helical type may be used only in application where the load tends to wind up the spring and are used in various electrical mechanisms, or spiral type. So wherever required, the load is tends to wind up the spring. So like this, the helical torsion spring shown and spiral torsion spring. So generally this type of mechanisms used in watches also. In olden days, in olden days clocks, this type of spiral torsion springs are used to store the energy, and then whenever you want to release that energy, you can easily use that energy. So due to the elastic nature of the body. So in this spiral type, where the load tends to increase the number of coils, and when made of flat strip are used in watches and clocks. So this is the this is a figure related to this helical torsion springs and spiral type. In first case, in torsion spring, where the load tends to wind up the spring and are used in various electrical mechanisms. In second case, load tends to increase the number of coils when made of flat strip are used in watches and clocks. Next, third type is laminated or leaf springs. So this type of springs are generally used in automobiles. So laminated leaf springs, also known as flat spring or carriage spring. So it consists of number of flat plates, so known as leaves of varying lengths held together by means of clamps and bolts. These type of springs are called as laminated springs. So it means the number of leaves, number of plates laminated to each other with varying lengths. So the diagram I will show you. So generally these are mostly used in automobiles. So after lamination, these all bolts are clamped. The all plates are clamped with the help of bolts. See, this is the laminated spring shown in this figure. So these are called as leaves or plates, flat plates, laminated plates or leaves. This one is called as master leaf. So different the remaining leaves varying length, all laminated together and then clamped with the help of bolt. So generally, these type of springs are used in automobiles to absorb the energy and act as a shock absorber. Next type of spring is disc or belly wheel springs. So these type of springs are consist of a number of conical disc. So number of conical shape discs are held together against clipping by a center bolt or tube. So shown in this figure. These springs are used in applications where high spring rates are required and compact spring units are required. The spring rate, high spring rate and compact spring units are required. So wherever less space is available there, this type of this type of springs, disc or belly springs are used. And here required high spring rate. Spring rate already that is d by d, the mean coil diameter, the ratio of mean coil diameter to wide diameter. So I will tell you in later slides. Next, special purpose springs. Other springs are there. These springs are air or liquid springs, or rubber springs, or ring springs, etc. So the fluids, air or liquid, can behave as a compression spring. These springs are used for special types of applications only. So that these type of springs are called special purpose springs. So special type of applications, very rare applications, this type of springs are used. So the fluids, air or liquid, is used in these springs and behave as a compression spring. So due to this fluids, air or liquid, the spring behaves as a spring. So next, what are the materials? The spring. The springs are mostly made from oil tempered carbon steel. These oil tempered carbon steel wires containing 0.6 to 0.70% carbon and 0.60 to 1% manganese. So contains carbon and manganese. So generally music wires is used for small springs and the non-ferrous materials like phosphor bronze, beryllium copper and monel metal and brass, etc. These are the non-ferrous materials and ferrous materials already explained in this line. Tempered carbon steel wires are used. The percentage containing 0.6 to 0.7 and then manganese percentage 0.6 to 1. So other terms really used in the compression springs very very important while problem solving or whenever you want to design a spring, you should know these terms. So very important terminology. In the first one is solid length. So what do you mean by solid length? The solid length means when the compression spring is compressed until the coils come in contact with each other. So it is in a compressed state. So when the spring is subjected to load, so the spring is compressed. But this type of compression until the coils come in contact, all coils come together in contact with each other. Now measure the length. Then the spring is said to be solid. So how do you calculate? The solid length of the spring is the product of total number of coils. It is denoted by N dash. And then the diameter of the wire is a small d. So the solid length of the spring is N dash into d. So where N dash is number of coils and small d is diameter of the wire. So like this, need to calculate the solid length. Next, free length. Free length is the free length of a compression spring. I'll show you the diagram. The length of the spring in the free or unloaded condition. I'll show you the diagram not here. So the free length of the compression spring, I will draw the length of the spring in the free or unloaded condition. So it is equal to the solid length plus the maximum deflection or compression of the spring. Suppose the spring is subject. Previously, this like this. So in this, the length of the spring in the free or unloaded condition. In this, there is no load. There is no load. So the length is called as free length. But when it is subjected to load, what will happen? It deflates some with some value. In previous case, in cellular, compressed until the coils come in contact. So whenever load applied, compressed. So this is solid length and free length. So solid length plus the compressed position plus the deflection, how much deflected or compression of the spring, and clearance between the adjacent coils. What is the clearance between one coil to another coil? So in already shown diagram in previous like this. So what is the clearance between one coil to another coil? What is the gap? In this is fully compressed state. This one is solid length. This one is free length. So how do you calculate this free length? So maximum deflection or compression of the spring and the clearance between the adjacent coils when it is fully compressed plus solid length. So mathematically we can write solid length plus maximum compression plus clearance between the adjacent coils. Also called as this clearance between the adjacent coils is clash allowance. So N dash D, already you know this one is a solid length. And maximum compression, delta max. So the spring can elongate compression up to maximum value. And then clearance between the adjacent coils, this is standard allowance are given to the springs 0.15 delta max. So we will get free length. Next, spring index. The term is, the spring index is, you can denote it by C. So the spring index is defined as the ratio of the mean coil diameter to the wire diameter. So capital D by small d. So where D is the mean coil and diameter of the wire. So in this diagram, so already you know, suppose the spring is, so the cross section is, circular. This wire diameter, wire D, and mean coil, this is capital D. So take the ratios and we will get spring index. And spring rate. Spring rate is also called as stiffness of spring. K is equal to load for deflection. So denoted by letter K, and is defined as the load required for unit deflection of the spring. So how much deflected for a given load, per particular load. So that is, you can measure with the help of this empirical relation, load for deflection. So W is the load and delta is the deflection of the spring. The spring rate is K is equal to W for load for deflection. Delta is deflection. Next term is pitch. So it is defined as the axial distance between the adjacent coils. So what is the distance, the axial distance between one coil to the next coil, immediate coil or adjacent coil, in uncompressed state, not in compressed state. So in uncompressed state. So whenever it is not subjected to any load, and not in a deformed position. So that adjacent measure the distance, that is called as pitch. So pitch of the coil measured with the help of this empirical relation. Free length upon n dash minus 1. So n dash already number of coils. And the free length, so already we have discussed in previous slides. And then pitch of the coil, you can write like this: free length minus solid length upon n dash plus d, wire diameter. So we will get pitch of the coil. So here given LF is free length of the spring, and LS is the solid length of the spring, and N dash is the total number of coils, and D is the diameter of the wire. So already shown in this, LF minus LS upon N dash plus D. So this LF minus LS is equal to free length. And free length. So here calculated the pitch by using like this, by using this empirical relation. Next, what are the stresses induced in the springs? Now, mostly the stresses induced in the helical springs are tensile and compression stresses only, due to the bending. The stresses in the helical springs of circular wire, T is equal to twisting moment. So due to this twisting moment, the shear stresses also induced in these springs. So torque twisting moment is equal to load multiply with mold multiply with the distance radius. So already you know pi by 16 into shear stress multiply with dq. This is the y diameter. So by using this relation, calculate shear stress AWD by pi dq, where d is the mean dia and small d is the y dia. So in addition to the torsional shear stress induced in the wire, the other stresses also will act. What are the? One is direct shear stress due to the direct load. And the second one, stress due to the curvature of the wire. So sometimes you may be neglect this curvature of wire also while doing problems. So sometimes they will give, so consider curvature of wire also. So that's why these two also are very important while problem solving. Direct shear stress due to the load and stress due to the curvature of wire. So direct shear stress due to the load, already you know, load for cross-sectional area of the wire, W by pi by 4 into d square. So this is, you can write 4W by pi d square. This is direct shear load. Next, stress due to curvature of the wire. And then the stress, the maximum shear stress induced in the wire is so tau is equal to, this is the total maximum shear stress induced in the wire, K multiply with AWD by pi dq. What is this K? This is wall stress factor. So wall stress scientists introduced this factor. You should multiply this factor while calculating the maximum shear stress. So 4C minus 1 by 4C minus 4 plus 0.615 by C. So what is C here? C is a spring index, that is a small d by capital D by small d. D is the ratio of mean coil diameter to wire diameter. So we will get relation K into 8WC by pi d square. You can write in other words also AW in place of C, capital D by small d divided by pi d square. So K AW capital D by pi d cube. See, another term is deflection. And deflection of helical spring of a circular wire. How do you calculate the deflection? So deflection is, by using this empirical relation, you need to calculate. Load upon K in the stiffness, K is equal to load upon deflection. So deflection is equal to load per stiffness. The stiffness of the spring or spring rate already given in here. It is a constant. So what is that value? AW into C cube into N by G into D. So already you know this axial load, and C is the spring rate, spring index, and number of coils, and G is the modulus of rigidity, and small d is the y dia. So like this you can calculate stiffness of the spring or deflection of the spring. Next term is eccentrical loading. So sometimes the load does not pass through its center axis. Those type of loading is called as eccentric loading. The load on the springs does not coincide with the axis of the spring. So it means the spring is subject to an eccentric load. So the load acting with the center axis is here and the load acting here with eccentricity. Okay. So this type of loading is called as eccentric loading, and it is said to be the spring is eccentrically loaded. So if eccentric load on the spring increases, the stress on the one side of the spring and decreases on the other side. So if it eccentric loading on the spring increases, the stress on one side, another side what will happen? Decreases. So when the load is offset by distance E from the spring axis, so then the safe load on the spring may be obtained by multiplying the axial load by the factor. So that is the factor shown here, d by 2e plus d. What is d here? Mean coil diameter, mean diameter of the spring. And e is the eccentricity value, that is distance. Next important term in springs is buckling. So buckling of compression springs are very important in design of springs. So it has been found experimentally. So when the free length is more than the 4 times of the pitch diameter or mean diameter, then what will happen? The spring behaves like a column. So it may be failed by buckling load. So I will show you diagram. So that you need to calculate that buckling load, that is buckling or critical loading, crippling loading. So whenever this the free length of the spring is more than the 4 times of the pitch diameter, then it is said to be buckled. The spring may be failed due to this buckling load. So do this calculate that causes that critical axial load, also called as buckling load. Buckle may be calculated using the following relation. So what is this relation? Critical loading into K spring rate and KB buckling factor, that is depending upon the ratio of free length to coil diameter and then free length of the spring. So by using this empirical relation, you may calculate the critical load or buckling of the spring. So in this diagram shown, one is fixed end, another end also fixed end. In this guided end and guided end shown, this the spring behaves like a column, like this. Like this buckling will be happen. So if increases this buckling load, so after some time the spring may fail. This phenomenon is called as buckling. So how to avoid this buckling? How to give some supports to the spring. Next term is surge in springs. What is this surge? So when one end of the helical spring is resting on a rigid support, clear, and other end is loaded suddenly. So one end is, the spring end is resting on a rigid support. One rigid support is there resting. When apply load suddenly, so then all the coils, all the coils of the spring will not suddenly deflect, not deflecting at a time. So that means not equally deflect, because some time is required for the propagation of the stress. So from one end to another end, it carries load from one end to another end and bottom to top and top to bottom. So it takes some time. So that all coils will not participate in this loading. So what will happen? So in the beginning, the end coils of the spring in contact with the applied load takes off whole of the deflection. It transmits large part of its deflection to the adjacent coils in the beginning case. In this way, what will happen? The wave of compression propagates through the coils to the supported end. From it is reflected back to the deflected end. The spring in contact with the applied load, it takes the deflection and it transmits the large part of the deflection to the adjacent coil. Next, that coil transfer to the next adjacent coil. Clear? So after that, after the end of the spring, what will happen? The wave compression propagates with support end from to the deflected end. So due to this wave, some deformation and some failures will be occur if the continuous like this. So the propagation, the wavelength of the propagation is very large, then the spring may be fail. This phenomenon is called as surge. So this results is very large deflections of the coils and correspondingly very high stresses. So under this condition, just possible that the spring may fail. This phenomenon is called as surge. It means some resonance will be occurred in the spring. Resonance already you know. So whenever the frequency of the object is matched with the external frequency, then the component will fail, the object will fail. So it means the vibrating body frequency is less than the external body frequency. So you have to maintain like this. So that's why in this case in springs you need to calculate the frequencies. So what is the natural frequency of the spring? So due to this property, the surge will be occurred. This phenomenon, the component will also fail. So the entire phenomenon is called as surge. So these are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.